Okay. Good afternoon. Hopefully you had a productive and also restful weekend. Today, we will pivot topics in a sense to something that's more written. And the goal of today is to give you some insights, pointers, verbiage, background on data analysis and the design of your population in support of homework number one, which is out and will be due a week from today. And so the goal of that assignment and the supporting in-class coverage is to get you to the point where you're designing a user survey, because I will collect those submissions and submit them along with some other information I provide for IRB approval. And we really need to catch the February cycle for the IRB board. They meet once a month. Okay? All right. Any questions? No? So before we begin, some administrative bits. Let me see. There we go. The reading has changed by a week from today. This is also in the Moodle site. I have a reading section. There's a supplementary document that I put on the Blackboard with the stats prefix on it. Try to make it easier for you to find stuff in the course resources section of the Moodle site. And it's Introduction to Descriptive Statistics. And so please make sure you're reading this stuff, keeping up with the reading. It's all sort of designed to meld together to help you to be successful. Project number 3, the AHA alarm. I had a typo in the slide that said project number 2 is due this evening at 11:59 and 59 seconds. If you are done, please hand it in early so you can do your happy dance, right? If you want to hand it in multiple times, I believe I've set the submission to accept 20 submissions. So you can submit again and again and again, but I will only look at the final submission. So the latest submission you submit, that's the one I'll look at. I'm not going to look through all 20 of your submissions. Homework number 1 is out on survey design, but please make sure you hand in what is due this evening. And if you're ready to hand it in, do it early. Don't wait until the last minute. Okay, any questions about project number 3? Did anyone change the song? No? No? Okay. All right, good. Spend your time on the task at hand. And if you have extra time, please, by all means, if you're musically inclined, have fun and play other songs. All right. So that being said, where we last left off, we talked about digital input, and we showed how it's different in terms of the anatomy of a basic Arduino program, how it's different from a sensor that requires digital output. And so we have some stuff up top where you define things. You have the 2 entry points, the setup routine and the loop routine. You start out using pin mode to set the direction for that particular digital I/O pin that you're using to support the device. And then in the loop, you're doing a digital read for that particular pin you've designated for your digital input, your sensor, and then you're doing something with it. Okay. Any questions? No? All right. And then, of course, we contrasted that with the buzzer, which takes digital output. And again, in our anatomy of an Arduino program, we have some definitions up top. We have our 2 entry points, the setup and the loop. In the setup, we use pin mode to set that pin for our buzzer that we're using on the board to be output. And then in this case, for our loop, we're setting the buzzer high and low to cause that pressure wave at a certain frequency that we perceive as sound. And again, please tinker with this. That's how you get to know these things. And I saw some of the chatter on Slack. Some of these components will fail. That's a part of life in any sort of electronics. And when they manufacture these things, these are fairly, dare I say, cheap, inexpensive components. They're going to break, and they're not going to be all perfect. What you pay for when you pay more for your components is all of the quality control and the better manufacturing and the more ruggedized components. I mean, you could pay $12 to $14 for that PIR sensor itself, one that is much higher quality than what we have. So don't feel bad, don't feel shy, don't feel anything. Components burn out, components are imperfect. That's just a part of the name of the game. Okay. Any questions? No? All right. We also talked about a preprocessor include when that particular so-called header file is one that you have written. And so this is almost like including a library in Java, an import statement. But in Java, everything's handled for you by the runtime. You pull in the definitions of those functions or quantities or definitions from the library. But in Java, the runtime loads the object files, the bytecode for those function definitions. And so in C++, or the subset of C++ that is Sketch or the Arduino, you pull in the definitions with the number sign include. And if it's your own header file, you use the quotations, open, close quote, with the name of your header file, making sure that it's in the same directory as your program, your INO. And then if you're using something else that's by the system, you have to make sure to have the bytecode for those libraries. But if you only have definitions, well, you just have the number sign include, and in this case, pitches.h, which is a set of definitions that make it programmatically easier to set the delays needed for the tone library, so you can use the notes by name instead of by the frequencies. Okay, any questions about this? No questions? All right. Okay, so let's go to the main topic of today. And of course, we're doing population survey in support of finding a problem or an issue that we can address with an IoT solution under the mantra of student life. So something that could conceivably improve or address some aspect of student life. And so we said when we talked about this idea of personas, it's a caricature, and this caricature must be something that you can instantiate within your population, be able to go out and find someone. And this caricature helps you to build empathy or walk in the shoes of the potential quote unquote customer whose issues you're trying to address. Now, in order to understand them, you're going to go out and do some research, the user survey that we talked about. So we're going to take a step back and talk about population in general, because it's really important to understand the people whose issues you're trying to address. And so population is a statistical term as well as a casual parlance, and it refers to, more formally, the collection of all possible units of interest. In our case, our population is fairly self-contained and identifiable. It's students at Clark University. But even still, with this set of students at Clark University, it's important to understand who they are and what their issues are, because depending on who they are, their issues might be similar or they might be divergent, might be different from one another. And so we're interested in things that might be impediments to student life, quality of life, and our focus is on Clark University. Now, you can imagine if it were the city of Worcester or Worcester County or Boston or all of Massachusetts, this would be a lot harder, but I still want to hopefully impart to you ideas that will help you design better user surveys. Okay. And so there's a quantity in statistics called a parameter, and more formally, a parameter is a descriptive numerical characteristic that talks about some aspect of the members of that population, those units of interest that you're enterprising to study. And some examples of this might be the average daily commute. Of all the students at Clark, there's an average amount of time it takes them to get from wherever they leave in their home environment to the classroom for whatever class they have in the morning, that first class. Also, another example, maybe the number of times per week you miss the dining hall. Dining hall is open for a certain block of hours. It does not work well for all students. And sometimes you miss a meal plan swipe. It's a waste of money, right? Okay. And there are all sorts of other parameters. And these parameters collectively define who is your population, okay? Now, the good news is these population parameters exist. They're floating out there somewhere in your population. That's the good news. And these are your so-called ground truth population parameters. If, and this is a big if, you could contact every single student at Clark University and ask him or her what is the amount of time that it takes you to commute to campus, yes, you could figure this out quite easily. But that if means it's really hard, even for a community relatively small like Clark's, because there's no way in the world you're going to get every single student at Clark University. It's impossible. So the good news is these ground truth so-called population parameters, the actual ones for the population, they're out there. But the bad news is you don't have access to it. Okay. So if you don't have access to it, what exactly do? You have to estimate. You have to take a mathematical guess. I won't say educated guess, I'll say a mathematical guess. And beyond the scope of this class is how you evaluate the quality of those mathematical guesses. That's a stochastic computing, shameless pitch for my class if I'm teaching in the fall. But the best you can do is make this estimate or mathematical guess from data. And you get that data by sampling, where a sample formally is your pulling of members from this population and you're getting this data from them. And that's what your user survey is purposed with doing. Okay. Any questions about this? Now, if you can do survey design really well, you could get a master's degree in this stuff, because not only do we care about it in this class, but businesses of all sorts are really, really interested in doing this well. Because if you don't have the right depiction and representation of your user base or your customer base, your product will not succeed. You'll completely miss, okay? And so we can think about the subgroups that comprise your population, because your population is not a monolith. And we'll talk a little bit about some considerations and leave the rest up to you. And so one easy description for structuring your population at a place like Clark University for the students body is to think in terms of your student status. You're a freshman, sophomore, junior, or senior. Now, of course, I'm simplifying this because you could be a first semester freshman, a second semester freshman. From a transcript standpoint and credits, because maybe somebody transferred, you might be credit-wise a sophomore, but in your major, you're a second semester freshman. Any questions about this? Does that make sense? Now, that's fairly obvious in an environment like this, and you choose your structure, what you're hypothesizing, guessing really, based on functional things that people do within your population. Another partitioning for describing subgroups in your population might be how you get to campus. There are some who are residential students, and when you sign up for parking, you learn this very quickly. They live on campus. And there are some who are commuter students, okay? That's another characterization that you might have. Now, of course, that's very different from your student status, okay? Another might be the place of origin where you started before you came to Clark. Some are domestic students, some are international students. And then maybe you have some that are kind of a little bit of both, but not the same as either, immigrants, okay? Now, all of the examples that I've given so far, these are so-called hierarchical populations. They're a collection of possible units of interest, and this collection is made up out of an assortment of subgroups. Now, of course, I started just with a one-level hierarchy. You have the whole group, one level, the partitioning, and these partitionings, for the sake of discussion, they do not overlap with one another. But absolutely, you can have a freshman who is an international student. You can have a commuter who is an immigrant. And so the membership to these groups that you hypothesize or that you invent or think about, you design, can either be overlapping or they can be non-overlapping. Which is the right approach? It depends on what you're enterprising to accomplish. And so this will require you to think a little bit about how different cohorts of people are arranged at Clark University in terms of the student population. Okay, any questions about this? Does that make sense? All right, so here's an example of the international, domestic, and immigrant population subgroups. And in this case, I'm acknowledging that the immigrant population, they're kind of international, but they're also domestic. And so in this case, I'm saying, well, this immigrant population, they share characteristics of both of them. When they're non-overlapping, you're saying they're distinctly different. And so how you choose to organize your subgroups that collectively comprise the population that you'll be studying is entirely up to you, but you need to think about functionally what it is you're trying to accomplish. Another one is the residential commuter off campus. Well, someone who's off campus, they're residential, they're right kind of at the campus, but they're also commuters. They might live off campus in university-owned housing or privately owned housing, but they're commuting because they're not in a dormitory, but they're also residential. They're right at the university. And so if you're thinking about pinch points or issues related to these characterizations, if these points are entirely unrelated to one another, you might have them as separate groups, non-overlapping. If they are related to one another, then perhaps these overlapping groups are a better depiction of what you believe the population is. Okay, any questions about this? No questions? Make sense? Yeah. Now this is open-ended and it's going to require you to think, and I don't have an answer sheet that says this is the actual population of Clark. This is going to be a research study, right? You're going to go off, think about it, gather some information, and make an educated guess. Okay. And so this question of how to structure the population is not just an academic exercise. You're going to need it to help you design your survey. And so your survey isn't just the questions you're asking, it's the time, location, and amount that you're using when you sample from your population. And I'll explain what I mean by that in just a moment. And so when you structure the population, there are lots and lots and lots and lots of demographic characterizations that they have for a campus community. And these are some of them. And there's a URL that talks about, Clark's Fast Facts and their college guides and stuff like that. But the one thing to keep in mind is that there are demographic characterizations that might seem obvious. I'll use the word visible, but there are several that are invisible. For example, just looking at somebody on the street, you don't know what their veteran status is. You have no idea. Or what their identity is, or the country of origin, right? So when you look at these sort of descriptions, don't make assumptions. And you want to think about those attributes that you can use to describe subgroups that comprise your population, both for the visible things as well as the invisible things. Okay? All right. And so when you pull members from the population and you sample, of course, you go someplace, so you choose a time, not necessarily at 9:05, but maybe it's morning, midday, afternoon. You choose a time and you choose a location and you contact people. It could be through an online survey equivalent, or it could be in person. And you pull this person from the population and you question this person. You collect data from him or her. Now you do it again, contact someone else. And you pull this person from the population, and this is sampling with replacement. You don't keep them captive. And then you get data from this person. And then you do it again, and you do it again, and you do it again. And the one thing you want to be careful of is if your sample is truly representative of the population that you're trying to understand. Now, in this case, our sampling was limited just to this location. Now, when I say this location, I'm being kind of loose with my terminology, but a location could mean I'm only going to interview students who pass through the second floor of the BP building. Now, you might have more computer science students, some math students, some physics students, versus if you're close to the theater building, I don't remember what it's called, you might get more art students that you contact. And so when you sample, what your population description is going to help you think about is this idea of time and location. Whom do you contact? Where do you find them? When and how do you contact them? In my previous university, the freshman classes were always early in the morning. And as you went to sophomore, junior, senior, you got to sleep in a little bit. Things were later in the day. So if you only surveyed at like 8:30, 9 o'clock in the morning, you'd have a higher number of samples from freshmen versus sophomore, junior, and senior. And so one of the things you do with this exercise is you develop a structure for your population for whatever is of interest. They can be overlapping, non-overlapping, and then you use that to tune the time and location, and this last one, number, for your samples. And so if you enterprise to get, for example, 50 samples, contact 50 individuals, you're more likely to get a broader swatch if you do maybe 10 of them here, 10 of them the other side of campus, 10 in the campus center, and so forth. So this is a tool to guide your thinking about the time, location, and number, because if your sample and what you garner from your analyses of this data you collect from your samples, if it's not representative of the population, you're going to make the wrong statement. Take, for example, if you were doing a phone poll. If you only phoned landlines to ask questions about product preferences, well, younger people are more likely to be cell phone only residences. And so if you only surveyed landlines about, for example, snacks or napping behavior, things like that, it's going to be not representative of a population that you might be enterprising to reach. Okay? All right, any questions about this? Does that make sense? No questions? All right. So then you use your population design, as I said, to guide your sample placement. And then once you collect all this data, you're going to analyze this data. Okay. And so don't make assumptions, right? Don't make assumptions, because the person that you contact, there are visible demographics, but there are many invisible demographics, things you would never know about the person unless you asked, right? So don't make assumptions. Secondly, when you're doing a survey, it's really important to explain your purpose, and you outline the structure of your survey so that the person you contact knows what he or she is in store for. And so you might say, working on a class project concerning student life, would you be interested in participating in a 10-minute survey? And so if it's a 5-minute survey, it really has to be a 5-minute survey. If it's a 10-minute survey, it really has to be a 10-minute survey. Now, if you're giving a reward for their participation, you actually have to give that reward for their participation and not rescind it should they choose to opt out during the survey. Okay. Now, I'm not advocating you give rewards. That can get expensive depending on, what the reward is. But these are just general considerations if you were kind of doing this, quote unquote, in the wild, in the real world. Okay. And so then you explain what you're going to be doing. And some of these questions might be open-ended. Some of these questions might be pick one. When do you usually get to campus? Morning, midday, or evening, right? When do you usually go to the dining hall? Morning, evening, afternoon, or evening, right? When do you usually have your classes? Well, mostly before noon, between noon and 3, or from 3 onward, right? So some of them can be multiple choice. Some of them, like a satisfaction, how happy are you with X, Y, and Z from a scale of 1 to 10, where 1 is completely dissatisfied and 10 is at the other extreme, ecstatic, right? And so you always want to explain what you're doing, because people's time is valuable. But if it's something that he or she cares about, my experience is they're usually more than happy to give you that 5 or 10 minutes. Okay? Any questions about this? Does that make sense? Yeah? All right. And then, of course, when you're going to start, you tell them you're going to start, right? Because if you just say, okay, we're doing this survey, and they don't know when it starts, it's just this awkward silence, and you're just wasting their time. All right. So the first thing you do when you get this data is you look at it. Seeing truly is believing. Now, when you see this data, it's going to help you decide on what functions to compute over it, how to summarize it. because it's these summaries that can give you a lot of insight. And these multiple summaries, or these functions you compute over it, or statistics, as it's formally called, allow you to make statements about the population of interest. And so a great example of this is what I like to call the pizza chart. And this is a geo-registered visualization. And what this talks about is for various national brands for pizza chains. These aren't the small mom and pops pizza establishments. For these big chains, what is most popular geo-registered in various parts of the contiguous United States, the 48 states. And so some things that are kind of curious, at least to me when I see this, along the West Coast from like Silicon Valley up through like Seattle, it seems that Papa Murphy's is pretty popular, just at the edges. There's a kind of pizza hole where there's nothing here in Nevada. And then if you go along the Northeast corridor where the Amtrak goes from Boston to DC, you see a lot of this blue, which is Domino's, and to a much lesser extent, CC's Pizza. And then when you see here from Georgia and going on to Alabama, going west, right at the border, you see a mix, a lot of Papa John's, but only near the border, which is pretty curious. Now, this other chart is a population chart represented as a relief map. The higher this mountain, if you want to call it that, the more population you have. And so here, this huge spike, that's New York City. And then here, this huge spike, that's Los Angeles. And so one of the things you'll see, if we kind of flip back and forth, there's a lot of population along the Northeast corridor. That's why it's the most popular route for Amtrak. Going from Boston to DC, there's a lot of population spike along that Northeast corridor route. And that coincides perfectly with the Domino's corridor. So for some reason, people in those really dense urban areas that abut one another, going from Boston to DC, tend to prefer Domino's. Go figure. And then if we look here in Las Vegas, there's a lot of desert there, not that many people live there. That coincides perfectly with our pizza hole. And so it's not worth it for them to place their establishments in that part of Nevada. So if you wanted to start a pizza chain, you'd better look at something like that and say, gosh, well, if nobody wants to touch that, maybe I shouldn't either, because perhaps it's not profitable and worth the effort. It doesn't mean that there's no pizza, God forbid, in those areas. It might be that they're better served by the small local mom and pop establishments. Okay, and this is just to say, when you have visualizations, a collection of visualizations, together, they tell you something about the area. For example, my wife and I, we do something called the Trader Joe's test, right? Because it seems everywhere there's a Trader Joe's, we usually like living in those areas. So we let Trader Joe's do all the work about studying areas, and we leverage that and say, where's the nearest Trader Joe's? And we have some radius around that we consider when we're considering where we're going to look at real estate. Okay? And so a collection of these visualizations together tell you something. For example, if you know the average commute time for various segments of the population, and you also know the number of times they miss the dining hall hours, maybe you find that those who get stuck in traffic more are missing the breakfast shift for the dining halls, for example. Okay, any questions about this? All right, so it's the collection of visualizations that make for telling a story that helps you understand the population better, this empathy that we talked about. All right. And so if we're going to talk about data that we collect from populations, there are different types of data, so we need to understand what they are. And so a so-called categorical object or categorical variable or categorical data talks about objects. Objects have names, and things like a cat, a dog, a truck. And so these typically describe distinct categories, hence the name categorical. And so you could say an animal is a cat and an animal is a dog. Now, some types of categories, and therefore categorical data items, have no natural ordering. They're so-called nominal variables. And so if we take a look at cat and dog, there's no natural ordering. Absolutely, you could sort them in order lexicographically, right? Because C comes before D. But that has nothing to do with seeing a picture of a cat and seeing a picture of a dog. You can't necessarily say, aha, this one comes first, this one comes second. There's no natural ordering to these nominal variables. And then some types of categorical variables are so-called ordinal. There is a natural ordering to them. And this is often more than not semantic. Take, for example, movie ratings. Movie ratings correspond to the suitability of the content of the movie for underage children, right? Or underage or minors. And so we have general, PG, PG-13, R, and NC-17. There is a natural ordering to them, and it's typically semantic, right? There's nothing about the image here that allows you to order them. It's what the meaning is that allows you to order them. And so there's a difference here. These ordinal categorical variables have a natural ordering, whereas these nominal categorical variables do not. Okay. Any questions about this? Oh, make sense? No? All right. And so there are other types of variables that typically correspond to some kind of measurement, and these are numbers and therefore called quantitative variables. These have a natural ordering. So if you measure, say, the length of a board, you measure the amount of gallons that a storage tank can accommodate, those are measurements. And these measurements, because they're numerical, i.e. quantitative, they have a natural ordering to them in numerical order. Now, for these quantitative variables, there's a dichotomy in terms of the value. Some are so-called discrete. That means they're countable. You can draw a one-to-one correspondence with the naturals with these different values in order. And some are uncountably infinite, meaning they're continuous, like a temperature, right? If I give you two temperatures, 1 degree and 2 degrees, what's between it? Well, 1.5. I give you 1.5 and 1 degree, you can always find something between it, and it never reaches a bottom, never reaches the primary elements. It keeps going. And those are so-called uncountably infinite. Okay, any questions about this? No? All right. And so there are several nuances, and I'll just walk through some of them. Some types of variables are numerical, but you can treat them as if they were categories. And I'll explain with these charts. So here on the left, your left, we have categorical variables, men and women. It doesn't matter what the ordering is. It doesn't change the meaning. There's no natural ordering. On the vertical axis, we have counts. Okay, those are numbers. And we see there's a certain count of the men, certain count of the women. Okay. In the next chart, the one in the center, along the horizontal axis, and it's also really important when you're describing a graph to help your audience understand how to interpret that graph with defining what the axes mean and what the values is significant about the values. And so here along the horizontal axis, we have the age of a car in years. My car is 4 years old, 5 years old, 6 years old, etc., in whole numbers. And along the vertical axis, we have the price of the car in dollars. Now, each of these dots says for a car of a certain age, what was the price of that car? And so here we order the years from the smallest to the largest. You can sort them, right? They're discrete and they have a natural ordering. And you notice that as the car gets older, the price of that car decreases. And so what this graph is telling you, it's saying effectively, what is the depreciation? What is the decline in value of a car as it ages? Okay. So here we have all quantitative data and we're sorting them, natural ordering. Now in this graph, they're talking about model years. Along the horizontal axis, we have the model year, 2010, 2015. And even though they're numbers and they order them in numerical order, in this case, they're being used as categories. A model year 2010 car, a model year 2015 automobile. What is the count? So this might graph along the vertical axis. This last graph on the right might represent inventory, okay? All right, any questions about this? And so this is just to say, even though we just got done talking about categorical, numerical, natural ordering, and so forth, there are all sorts of nuanced variations of these things. It's not completely crisp. Okay. So let's take a look at different chart types, how you might plot various measurements, types of data that you collect from your survey. Now, a bar chart derives its name because it has these colorful bars, and it's typically used to describe counts for categories. Along the horizontal axis, we have categories. In this case, it's the seasons of the year, spring, summer, fall, winter, and they have listed it in some order. You didn't have to do it this way, but it's visually pleasing to talk about the seasons of the year, starting with spring sometimes, but it didn't have to be this way. And along the vertical axis, it talks about the number of children. And from the legend, it talks about for a particular family, in what season were children born, how many children in each of them. For whatever reason, someone might want to track that. Go figure. I don't know why, but there's our graph. Now, the other thing you can use a bar chart to do is to describe relative relationships between things. In this particular chart, they talk about the number of employees for various large national companies. Now here, they list along the horizontal axis, different stores, Walmart, Yum Brands, which is like Taco Bell, and I can't remember the other ones, KFC, Taco Bell, and so forth, McDonald's, some non-food places like Kroger's, Target, Home Depot, HP, and so forth. Now, the interesting part about this, these are categorical variables, so there is no natural ordering. But what they've done on the vertical axis is depicted as the height of the bar as the number of employees nationally that each of these employers has. And I think this was in 2013 or so. Yeah, 2013. And what they've gone ahead and done to make it visually pleasing is they've reordered these categories, not based on alphabetic order or some arbitrary order, but they've reordered them from the largest employer down to the smallest employer among the considered employers. And the reason for that is because it looks nice. You can say, this one is the biggest, that one is the middle. It allows you to make other statements. So absolutely, you can use bar charts to represent categories, but you can take advantage of the fact that there's no natural ordering to rearrange it to make statements that are important to you. Okay? All right, any questions about this? No? All right. And so you can take these charts, and if it's important to you, you can recast it through a transformation to talk about the relative frequency. And this is where we get into probabilities. We take our bar chart for that family, and then we divide the counts along the vertical axis. We divide it by the total number of samples that we have. And the same chart here with counts now becomes proportions by dividing each of those counts by the total number of children. And this is important if, for example, you talk about influence. You know, you can say so many percent of the population under consideration does the following or is in the following category. And maybe it's a case where you're trying to decide where you should direct your resources, and you want to direct or invest your resources in those units that are the largest proportion of the population under consideration, for example. Okay, any questions about this? So you can transform your charts in order to make other types of statements. And then lastly, the pie chart. Now the pie chart divides the pie into slices to represent proportions. Now, instead of a pie chart, you could alternatively cast it as a bar chart using relative frequencies. But the pie chart is good for making comparisons between those different proportions. Now here in this particular bar chart, it talks about the weekly average time, what activities college students engage in. Now, of course, it says sleep 8.7 hours. I don't know how true 8.7 hours a night is, but that's the numbers that they got. And I don't know which students, where it was, how many students, and all that stuff. But nonetheless, you can very easily look at the relative proportion, and they've annotated each one of these slices with the raw numbers. Okay. Any questions about this? Okay. And so it's entirely up to you how you visualize. Certain visualization types are good for certain types of things. And so this one is called a scatter plot. It's a Cartesian plane. And in this particular scatter plot, or in the scatter plot approach, each one of the axes represents one of the variables of measurement. And so in this case, you're depicting the relationship between two different things that you're measuring. So for example, the average commute time might be one axis, and the number of dining hall days that you've missed or meals you've missed, right? And so when you plot a point, its projection along each axis is that particular person's values for average commute time in that example, and the number of dining hall meal misses. Okay. Now, in this example, this is another scatter plot, and this is an analysis of college football team, national college football team rankings and head coach salaries. Along the horizontal axis, we have head coach salary, and along the vertical axis, we have the rank. Now, this rank is a little bit wonky, right? Because you're used to saying number one, number two, number three. In this case, you'll notice the lower ranked teams have a higher value along the vertical axis. The higher ranked teams have a lower value. And so lower in this graph means they're a better team. Their ranking is higher, right? It's a little bit weird to reverse it, but that's the way they've chosen to do this. Now, one of the things you can see, if we take an individual data point, we see that, okay, if you're ranked around 20, right, the salary is like, looks like 300, maybe close to $1 million a year. But you notice if your rank is like 1, your salary is way out there, $6 or $8 million. Now that just says that there's something about the relationship between ranking and head coach salary. Now I'm not going to comment on the socially redeeming or non-redeeming qualities and how colleges spend money on one thing versus another. That's a discussion for a different class. We're just talking about the data and how the scatter plot can represent relationships between two measurements. Now, if we draw a so-called best fit or regression line, we're basically taking a function, in this case, y equals mx plus b, and we're finding the line that is the closest to all of the data points. And we won't talk about those algorithms. I'd be happy to do it in another time in another place. And what this regression line or linear fit tells us is specifically what is that linear relationship, and it's captured by its slope. And what it says is that if you take a unit step increase in one variable, salary, what happens? There's a unit step improvement in the ranking. And those sort of relationships are used for things like real estate, for salaries, for all sorts of stuff. And so you can take your raw data, you visualize it, and then with an analysis like a regression line or linear fit, you can make a statement about how some phenomenon between two variables behaves as it changes. Okay, any questions about this? No? All right. And so the line chart is a type of scatter plot, but the points are ordered in some natural fashion. Now this represents share price. I can't remember if it's average share price for Apple or if it's the closing price or open price, but along the horizontal axis, we depict all of those days over which we take measurements for the share price. And along the vertical axis, we have the share price in USD, US dollar. And we can take these points and we connect them, one point to its neighbor going to the right over time. And it tells us how this security behaves coarsely on a day-to-day basis. And so here, what this line part gives us is a kind of interpolation. What was the value between these 2 points? Is it perfect? Absolutely not. But you can look at these trends and say, is it going down during this day? Is it going up during this day? Or is it relatively flat? Now we can take this line chart and we can fit a regression line to it, the scatter plot, where the regression line in red gives us the overall long-term trend, but the individual segments from one day's measurement to the next gives us the short-term trend. Okay, any questions about this? No, does that make sense? And so all sorts of visualizations can tell you all sorts of things, like this line chart. You can plot more than one measurement along the line chart. And in this case, along the horizontal axis, we have all the months representing a year, January to December. Now, of course, maybe if you were in agriculture, it might be over a growing season. Or if you were in a different industry, maybe academia, it would be from September to August the following year. And on the vertical axis, we have temperature in degrees Fahrenheit. And so we have measurements of temperature for a calendar year from January to December for 3 different locations. In the blue, we have Asuncion. In the red, we have Pueblo in Colorado. And in the red, we have Tianshui, right? Now, one of the things that stands out is if we look at the line chart for temperature, well, going from January to February, it increases. That's for Pueblo and Tianshui. And for Asuncion, right, from January to February, going on the first half of the year, it's decreasing. And if we look at the shape of these line charts for the blue and the red, Pueblo and Tianshui, we notice that their temperatures are very similar to one another. So if you wanted to, for example, start an agricultural operation in Tianshui, and you had some crop that grows well in Pueblo, well, that would be a great place to grow it. The other thing that we notice is that the high temperature in Pueblo and Tianshui is the low temperature part of the season in Pueblo, in Asuncion. Now, that probably means that they're in different hemispheres, because in the southern hemisphere, our summer in the northern hemisphere is their winter, right? And so certain crops will work together in Tianshui or Pueblo, but probably wouldn't work somewhere else. So you can look and compare and contrast categories of behavior of different areas with this type of graph, okay? So it's a line chart, but we put a number of line charts for different measurements together, and now it allows us to categorize things and group them together based on some quantity of interest. Okay, any questions about this? That make sense? All right, let's see what time we have. So one of the things that we do when we collect data is we want to summarize it. And we summarize it by computing statistics or functions over data. And these functions over data give us a compact representation of all of the information that we've collected across a group of interest. Now, one of the sample descriptive statistics is called the sample mean. The sample mean is nothing more than the average. Its notation is X bar. And the sample mean, and this alludes back to this idea of the ground truth parameters that are hidden from you, it's a good mathematical guess for the average that's really happening in the population. Now, there are some rigorous theoretical things that show that this is true. We will not cover that in this class. That's stochastic computing. All right, another shameless plug. Now, the sample mean has an issue. It's unstable, meaning that if you have a bunch of measurements, yes, it'll show you the average, and it's a really good mathematical guess of the true average in the population. But depending on how you're sampling, sometimes you get typical values. Other times, your sample mean includes atypical values or so-called outliers. Now, the sample mean changes quite a bit when you give it an outlier, an atypical value. That presents us with a problem, because let's say you're taking average commute time and most people live within, say, 10, 20 miles of campus. All of a sudden there's this one person, and I know a faculty member who does this, who drives from Rhode Island. That one measurement is going to move what your average is quite a bit. It's going to skew your results. And so the median is a solution for trying to get more stable values for what is notionally typical. when you're making these mathematical guesses. And so what is the median? The median refers to the middle measurement, whereas the mean is your average. Now, from a probability standpoint, the mean represents what's called the center of mass of your distribution, and the median is just the middle point in some ordering. Okay. Any questions about this? No? Make sense? No? And so how do you compute the so-called sample median? Well, to be in the middle, that means you are exceeded by half of the measurements, and you are preceded at the same time by half your measurements. And so if we had some measurements, and let's say it was commute time, or doesn't matter what the quantity is, and these measurements were 1, 4, 7, 9, and 11. So the first thing you do is you sort them in non-decreasing order or non-increasing order. Either they get bigger or stay the same, or get smaller, stay the same, based on what you're trying to determine. And then you take the one in the middle of your ordering. Now, if we look at this, okay, half of 5 measurements, that's 2.5, you can round it down to 2. It's smaller than 2 measurements. At the same time, it's larger than 2 measurements. That's exactly the sample median, denoted by M hat. Okay, any questions? No? Now, what happens if you have an even number of measurements, like 4? Well, your sample median is synthesized from the quote unquote 2 middles. Now, in this case, we have 4 and 7, our 2 middles, and we're taking the average between the two, which is 5.5. And so you have a scheme for computing this middle, regardless of whether or not the number of measurements you have is even or odd. Okay. Any questions? No, no questions. You're all pretty quiet. All right. And so one of the things we're concerned about is the shape of a distribution. And a distribution is nothing more than a depiction of the values of interest that a measurement can take on along the horizontal axis and the probability or relative frequency at which those values will occur. So if half the time, a particular value, 5 minutes of commute time, if half the time that measurement is going to come up, the probability of 0.5 of 5 minutes commute time will be 0.5. And so one of the things we're concerned about with your probability distribution is its shape, because the shape describes the dataness or the data behavior. Those values that more frequently occur, the important values, are the ones that have a higher probability. They're going to come up more and more and more than the other ones. So when you have the median and the mean, a so-called symmetric distribution is one where the median computed from the samples, like we just explained, is equal to the mean, which your X bar, your average, is a good mathematical guess for. If the two are one and of the same or close enough, then that's a so-called symmetric distribution. And what that symmetric distribution means is that the common values, those values that have the highest probability, the more frequently occurring values, the median estimates it spot on. It's a really good approximation for it. Now, you have two pathologies that can occur. One is an overestimate and one is an underestimate of common values. And so here we have, in the center frame, we have the median is smaller than the mean. And what does that mean? No pun intended. It says that you're overestimating the most common values. Here, we see that the most common values are those associated with the largest probability. Those are the values in this region. But when you take your mean, your X bar, your average, which is a good mathematical approximation for the unknown mean, it's going to overestimate. So if you said, what's my average commute time? And it said 5 minutes, it's really more commonly less than that, right? It's overestimating. That's called skewed right or right skewed distribution. The converse, a skewed left distribution, here we have the median is greater than the mean. So that goes to underestimation. If you were to compute your average commute time and it said 5 minutes, in reality, most commonly it's greater than that. And so one of the things you want to and can be useful when you're looking at data is to determine the skewness of your distribution. What are the preferred values, most commonly occurring values, and is there an underestimate or overestimate when you compute your averages? Okay. Are any questions about this? That makes sense? Okay. Now, I'd love to get into the problem stats and the rigorous theory behind it, but again, that's not the purpose of this class. Okay. So you can generalize this median. The median, we said, was the middle point among all of the possible values that that can occur when you sample, when you order them. You can generalize this idea of a median. You can consider in your distribution different values that partition your probability into regions. Now, for a probability, in order to be a probability, okay, I feel like I'm shouting. It's going to come back on again. Oh, probability adds up to 1, right? There it goes. I was expecting it. And if you take the area under the curve for any probability, by definition, the area under the curve has to equal 1, right? All the probabilities together for all the alternatives has to sum to 1 or it's not a probability. And you don't have access to all the tools from prob and stats. Now, that being the case, there are some values from all the values that you can observe that separate or partition the area under your probability into certain percentage parts. Now, the values here, Q1, Q2, and Q3 on the horizontal axis, these are the so-called quartiles. They're called quartiles because the area under the curve for each region is 0.25 or 25%. Now, when you see things about scores and you hear this person is in the 90th percentile, that's a generalization of the median. And you can divide up your distribution into arbitrary parts of arbitrary sizes, 25%, 10%, 90%, what have you. And so this generalization is called a quantile. And a so-called P quantile corresponds to a point such that if you took the area under the curve up to that value for the probability, it's going to equal that proportion P. And so if we had, for example, the 0.9 quantile, that would be a value such that if you took the area under the curve, that would be 0.9, 90% of all the probability. All right, so what does that mean? It means if you randomly pick a value, 90% of the time, it's going to be less than X. And that's what they do with things like SATs and GREs. Your 90th percentile. That means if you randomly pick somebody who took the exam, 90% of the time, their score will be less than you. And conversely, 10% of the time, the score will be greater than you. And so you use it to evaluate the relative value of a measurement among all the possible values under consideration. Okay? And so if your commute time, there's a term called a supercommuter. If your commute time is, I think it's 2 hours or more, you're probably in the 90th, 95th percentile, a so-called supercommuter, somebody who travels a really long time. And there are people who do that, travel long distances over long amounts of time. And conversely, if we look at it notationally, this probability of X, big X, that's a random variable, being less than little x, that's a value, that is a concise way of saying the area under the probability curve. Okay. Likewise, we can characterize those values that exceed as probability of random variable X greater than value X. There's something called a sample P quantile. Now, this quantity, the quantile, is a theoretical quantity, but if you do it from samples, there's an equivalent called the sample P quantile. And what is that? Sample P quantile is that number, and remember when we talk about samples, we sort them in non-decreasing order, so they get bigger or stay the same in sorted order. It's that number that exceeds at most 100 times P, and that's a percentage of the measurements. So the median is called the 0.5 sample P quantile. So if 0.5 is P, we multiply by 100, that's the 50th it exceeds at most 50% of the samples, which is exactly what our definition of the median was. Okay, any questions about this? Does that make sense? All right. A gamma percentile is another way of talking about it by using a percentage. And you'll notice here, they multiply by 0.01 to convert it back to a proportion. Okay? All right, any questions? No questions? That makes sense? Okay, so please take a look at that supplementary document I have in the reading. You don't have to super study it, but just familiarize yourself with some of these summary statistics. All right, so if we want to rename the median, there are many different ways we can talk about the median. It's the 0.5 quantile or the 50th percentile. And this other special name is called the second quartile or Q2. So the first quartile gives you the first 25%. Second quartile gives you the second 25%. 25 times 2 is 50, 50% of the probability mass. Okay. And so there are other things that people are interested in when they summarize the measurements that they take from their samples. One of them is how much these values vary. If you are measuring, for example, the share price of a stock every day over the course of a month, people are concerned with securities that wildly vary. Maybe, it's $100 plus or minus some large amount, or $100 plus or minus some small amount. That variability in the financial community is called risk. And in the statistics community, it's called variance. And what this variance describes is the dispersion or the spread, how wide these values are that you can encounter when you're making measurements. Here in the red or pink curve, the measurements, the values under that probability is much more broad than the values under this blue probability curve. And how you measure the so-called sample variance, S squared, 1 upon n minus 1 times the sum of the squared difference between each measurement and the sample mean, X bar, okay? And so what this does is it tells you if S squared is a large value, your individual measurements, when you take them, what's your travel time? What's your travel time? What's your travel time? 5 minutes, 2 hours, hour and a half, 3 minutes, 10 minutes, hour and 45 minutes. They're going to vary very broadly. If S squared is small, they're going to be small, 10 minutes, 12 minutes, 9 minutes, 10 minutes, 15 minutes. It varies less broadly. Okay. Any questions about this? No? All right. And so this variability or dispersion is called your sample variance, and the sample variance, S squared, and it's not a typo, 1 upon n minus 1, is a good mathematical guess for the actual variance for your population, this parameter that you don't have access to. And the reason for this 1 over n minus 1 instead of 1 over n is because this is so-called an unbiased estimator, meaning that by the theoretical analysis, I'll say it this way, it's exactly equal to this population quantity that you don't have access to. So this is a very good mathematical guess. Okay, any questions? But there's a problem here. When you talk about variance, you'll notice here, we say X minus each measurement minus the sample mean quantity squared. So if we were to talk about the average commute time and we measure the sample variance, it might be something like 17 minutes plus or minus, and with a variance of 100 minutes squared. What in the world does 100 minutes squared mean? It's kind of hard to wrap your head around what that means because the unit is very different from the unit for the quantity of interest. If someone said, how's the temperature going to be today, the weather? Well, the weather is going to be on average 37 degrees with a variance of 144. Huh? Do I bring my t-shirt or do I bring an extra sweater? What does a temperature degrees squared mean? And so the standard deviation was intended to repair this issue, to talk about variability, but express it in the same units as the measurement quantity of interest. And so the standard deviation, S, is nothing more than the square root of S squared. So you take your variance, take the square root of it, and this is now your standard deviation, and that expresses the unit that is same as the measurement. So if you said, what's the temperature today? I said the temperature is 37 degrees plus or minus 12 degrees. 12 degrees. That's understandable. It's in the same unit. What's your average commute time? It's 17 minutes plus or minus 10 minutes. Okay, I can understand what plus or minus 10 minutes means. And so the purpose of the standard deviation, sample standard deviation, is to express a notion of dispersion or variability using the same units as the quantity, measurement quantity of interest. Okay, any questions? Questions? No? All right, we have about 5 more minutes. There are other ways to measure dispersion, and unfortunately, well, there's good news and bad news. The sample variance, S squared, and the sample standard deviation, they're excellent mathematical guesses of these population parameters that you don't have access to. But the bad news is, just like the sample mean, these things are unstable. If you give them an extreme value, an unusually large or unusually small value, they're going to move too much. So you can have an outlier, the supercommuter that we talked about, that's going to skew or corrupt your results, right? And so something called the interquartile range is not sensitive to these outliers, not as sensitive as the variance and the standard deviation. And the interquartile range is nothing more than the difference, the numerical difference between the third quartile, Q3 value, and the first quartile. And so the IQR is just the third quartile minus the first quartile. And if you think about it, if this distribution is more dispersed, this curve maybe stretches all the way out here and all the way out there. That means the quartiles will be further apart from one another, and therefore the difference between Q3 and Q1 is going to be greater. So it kind of makes intuitive sense that interquartile range is a good proxy for dispersion. Now, the good news also is this is less brittle to extreme values, be that extreme large values or extreme small values. And so this interquartile range, computed from the samples, IQR hat, is nothing more than Q3 hat from the samples minus Q1 hat. And it's presumed that you put them in sorted order, in non-decreasing order from smallest to largest. And there are other reasons people might do it from largest to smallest. And so this interquartile range has an interesting property that if you take Q1 and you take Q3, that 99.3% of all of the values that you will encounter are within 1.5 IQRs below and above Q1 and Q3. And so you can use this in a data-driven way to determine, is this 2-hour commute, the supercommuter, is this person an outlier? Because if the person's measurement, that sample measurement, is extreme, how do you determine what extreme means? Well, now that you know, this is more than 1.5 IQRs above or below Q1 and Q3, then you can say, you know what? This is so atypical, I'm going to exclude it. I'm going to reject it. And that's exactly what outlier detection is intended for, because without it, you're going to let this one person among 3,000 people at Clark have a bigger say than he or she should in terms of what is typical for commute time. And that will absolutely royal mess up any statement you're trying to make, and therefore any decision you make based on that statement. Okay, any questions? No? All right. So 99.3% of the population values that you're going to get from samples are 1.5 IQRs away from the quartiles, namely Q1 and Q3. So let's have an example. And so the quartiles are those 25% points, and we have some measurements. I've just arbitrarily selected them 1 through 12, and we put them in non-decreasing order. We identify the quartiles. So here is Q1. It exceeds at most 25% of the values. Here's Q2, the median, exceeds at most 50%. Here's Q3, the third quartile, exceeds at most 75% of the measured values. So now we're going to take the interquartile range. That's Q3 minus Q4. So that's 10 minus 4, that's 6. So the interquartile range, IQR, is 6. If our IQR is 6, 1.5 of those IQRs is going to be 9. 6 plus 3 is 9. So now we then take Q1, which is 4, and we subtract 1.5 IQRs. Then we take Q3, which is 10, and we add 1.5 IQRs. So we take Q1, subtract 1.5 IQRs. So that's 4 minus the 9 is equal to negative 5. Then likewise, Q3, we add 1.5 IQRs. That's 10 plus the 9 is 19. So it says that for whatever system this was, if we continue to sample 99.3% of the time when we sample, we're going to get a value in this closed interval, -5 on the low side and 19 on the high side. And that's a rigorous statement. And so outlier detection is really important to determine whether or not some of the samples are atypical, because if you're going to design a solution that is amenable to the vast majority, you don't want to let your results be dictated by a relatively small number of people. Okay, any questions? Does that make sense? All right. So that's all I had to say for today. We're right up on 4 minutes ahead or 3 minutes ahead. So we'll meet up here again on Friday in the morning session. And in the afternoon session, we'll have an exercise for what's called ideation and helping you look at populations. I just have to go to Staples and get a lot of Post-it notes. All right. So that being said, I will see you all on Friday. Have a great week. Question? Is a what? Friday? Oh, what's a wellness day? Oh, all right. Oh, is that a Clark thing or? All right. I see. Ah, is that, huh?